Ladies and gentlemen, it's Wednesday afternoon in this great, wonderful place we call high school. Yay. The objective today is to make your head hurt. So let's see if we can accomplish that goal. Yeah. Whoa. You can't say that just the looks of your head makes people hurt. Yet that is not what you need to be saying. So let's pay attention to the problem. Each time a child inserts a quarter, it's 7 candies, right? Now, that's important information. This 15 pounds of candy, well, that's how many pounds holds in that thing. And it says 180 pieces per pound. So we can know how much they put in it, right? Good. So, I need to take said information, and I need to do something with it. It says, represent the number of candies in the machine for any given number of customers, right? At about how many customers will there be before the machine is empty? Now that is some math, right? Yeah? We got to do some math there. So, represent the number of candies in the machine for any number of customers. So how are we going to do that? Go. Make the total. Well, how'd you get the total? 180 times 15, which is what? 2,700. That's pieces of what? Pieces of candy. Now, okay, so I know how much candy's in there. Yay. Okay, so what do I do with that? Huh? Divide by 7? This said, represent the number of candies in the machine for any given number of customers. Okay, listen, we got to be able to write an explicit sequence, right? Anybody? What's this? Now, watch what I'm about to do. This is great. See, you would have thought A1 was 7, right? No? What did you think A1 was? 27 what? It's 2,700. Is it? Really? Oh, I like the way she thinks. So, that's what? That's zero term, is it not? Yeah. Because if it's completely full, has anybody used it? No. But but let's look at the equation. The equation is in what term? First. Which is what? Oh, love it. 2,693. That's first term, guys. Okay? Now, did it start to unfold and you're like, oh, I get it now? Yeah. You see how you sometimes you got to take information, you're like, sometimes it's smoke and mirrors? Right? No? It's not smoke and mirrors? It's just like one big old mess. Help me get through it, right? No. Guys, come on. Y'all got this. Okay, you ready? So, A sub n, that's any customer, right? 2693. What's D? The difference, the common difference. So what is the common difference? Not 7, but what? -7. Y'all agree? Okay, why is it -7? Because you taking it away, Mr. Comer. Okay. Hey, you want to prove that this is correct? You want to prove it? Yes, we know we want to prove things in math. Let's for grins and giggles, let's just kind of nerd out. You ready? In the beginning, A sub 0, right? Now, that would be 2693. That gives you -7 times -1, which is 2693 plus 7, which is How about that? What do you mean? Why did I put 0 there? Who did 0 take the place of? Who did 0 take the place of? Thank you. So it's got to take the place of who? Yeah. That's the whole reason that it's there, right? So did we prove that our equation works correctly? Yeah, good. Yeah, all right. So first person puts their money in there, right? We know we ought to have how many candies left? We ought to have 2,693 candies, right? You agree? So let's look at the equation. If I put right here, if I put in the equation right here, if I'd solve it in terms of a sub 1, right? Y'all said that we have to have 2,693 candies left in my bowl, right, in the thing, after the first time, right? So when I plug 1 in for n, what's 1 minus 1? 0. What's -7 times 0? So what am I left with? 2,690 what? Thank you, 2,693, right? So have we checked it for the first quarter? Yeah. Now, this may have made you say some ungrateful, mean things while you were thinking about this, about the opportunity in math today. But what I've got to get you to understand is this. This wasn't as hard as what you initially thought it was. You got to know what it's giving you and then what to do with it. Okay? Right? So you've got to be able to be smart enough to read it, figure out the information that they're saying, discard what isn't good yet, and then see from there. Right? This is a wonderful thing. There's my red. The red is the equation, right? At any time, I can tell you how many candies are in there. That is so cool. Did you know that there was equations like that that you could write that would do that? Now, you could write the simplified version very quickly, couldn't you? A sub 0's term. How could you write the A sub 0's term quickly? What would it be? Anybody? Well, if I distribute the -7, right, I'm left with what? Aren't I left with that in terms of 0 term? In the beginning, how many do I have? How are they decreasing? They're decreasing by how much? 7 each time. So that's the slope, right? That's really what you're doing, right? If I were to distribute this would be -7n. And of course, -7 times -1 would be a +7. 2693 plus +7 gives me 2700. So it's really not that difficult to get back to a 0 term, right? Are you expected to be able to write a first term explicit equation and a 0 term? Yes, you are. But once you write that first one, all you have to do is distribute the D, combine like terms, and you're done, guys. Do you understand? You're done. Yes. All right, so the question was, why wouldn't it be 2700 minus 7n? Well, here, let's look at this. What's the difference between the blue and the black? Huh? What's the difference between the blue and the black, guys? They switched it around. No. I want to know what the difference is.
Oh, it went from a negative to.
Buell? What do you mean there's nothing? What allowed me to just swap them? The what? Commutative property of who? No. It only, these properties only apply for multiplication and, no, addition and multiplication. This is commutative property of addition. What's 1 plus 2? What's 2 plus 1? You see what I'm saying? So when you swap this around, does it change anything? No, it does not. So how do we do? Y'all good? Why do you think we do negative 7n plus 20 plus 2700 compared to this? Well, why do we prefer the blue over the black? Helena? No? You don't know? Phone a friend. Phone a friend. Who do we go to next? Oh, Elijah. Friends like friends. Okay, see, that's much better. Well, failure's the first attempt in learning, so that's good.
So, like you said, like commutative property of addition or addition and multiplication, and that like top looks like division, and one bottom looks like subtraction. So that one is easier.
Are you sure you heard the question that we were asking? It's very evident that you were not paying attention to the question, so pay attention. Why is it that the blue is preferred more than the black? Now, they're both right. They're both right. If I was teaching college mathematical modeling, I would do the black. If I was teaching college algebra, I'd do the blue. Why? Formula for what, my dear? No, it's not a formula. It's an equation. Nope. You gonna sit back there and keep the answer to yourself, or you gonna say it? It's slope-intercept form. Lazy. Now do you see it? See, a sub 0 is an output, right? That's why. Here's your slope, -7. There's your y-intercept, start at 2700, right? That's why the blue is preferred. Now the black, well, that's just contextually, right? Because we take the total minus some times n, right? Negative n, right? So contextually, that's the difference. Very good, though. I know, but you wouldn't have learned that. And I wouldn't have learned this. Okay, represent the amount of money in the machine for any given number of customers. Have we done that? Yes, we have. We have chased it all the way. Now, here's the thing. Because I'll tell you something. We do not like thieves. We do not like thefts. So, to avoid theft, the store owner, it should be the store owners don't, okay, sorry. The store owners don't want to let too much money collect in the machine, so they take all the money out when they think the machine has about $25 in it. The tricky part is that the store owners can't tell how much money is actually in the machine without opening it up. So they choose when to remove the money by judging how many candies are left in the machine. About how full should the machine look when they take the money out? Okay, he says a fourth full. Why? No, he's got to explain his thoughts. You start with 2,700.
Okay, no, actually, $25.
Why $25 times 4? Okay, good. Why is that important? Because that's just simple stuff. You can't say that in a math class because everything is simple to me. I mean, it's just like, why didn't y'all understand that problem? It's so simple. Now, that wouldn't be right, now would it? So, my question is, why are we taking $25 times 4? Go. No. No. Huh? 4 quarters is $1. Okay, where are you going with that? Multiply that, they give you the number of quarters, right? So that's 100 what? Okay, why is getting it back to 100 quarters important? If I want a piece of candy, how do I get a piece of candy? Oh, I put a quarter in. So I put a quarter in, I get some candy out, right? That's why I need to know $25 back to how many quarters. That's 100 quarters, right? Oh, okay, so that's 100 quarters. So 100 quarters, 100 quarters. It's what? How'd you get that? Oh, wait. So we're going to do it, I know 700 is the same as that, but you got to show how you got there, right? That's 2,000 candies, right? $25 is 2,000 candies still left in that machine. So how could it be a quarter? Is it, you said quarter empty or quarter full? Quarter empty. Huh. Is that correct or not? Really? I'm sorry. Let's see. Hold up. That would be 2,000 over 27 what? Wouldn't that be? That's part over what? Whole, right? That fractions, you learned that in 3rd grade. Part over whole, right? So what is 2,000 over 2,700? Huh? It's not a whole number. Oh, excuse me. 0.74, which means, if you look at it from a percentage, 2,000 candies left is right around 74% full, right? Which would mean that, ladies and gentlemen, it is a what? Quarter, roughly. But could we just say a quarter? No. You've got to back it up with your what? Yeah. You've got to mathematically prove why you're saying what you're saying. Now, I didn't do anything difficult. All I done was took 7 turns, seven of them, and I had 100 turns, right? That's 700. Took that away from it. Got 2,000 candies, right? Left. Excuse me. 2,000 candies. Part over whole. I got a decimal, right? That's how much is there, percentage-wise, right? 0.74, which is 74%. So roughly about 3/4 of it, right? So a quarter of it empty should be about 25 bucks. Now the really cool thing is this. If the guy is really paying attention, or whoever, I say guy, whoever's taking the money out of it, if they're really observant, they can get really, really precise. They can get very close to $25 every single time that they empty the money. How? Huh? I can't hear you. What? No. See, the guy's not going to sit there all day and watch people buy candy, is he? See, that, I mean, he's got stuff to do, so we can't do that. I mean, come on. How can he or she precisely gauge so that it's right around $25 every time? They can't do this, right? Lick your thumb and put your thing out. No, that's kind of what? Yeah, you're dancing all the way around it. You're on the right track, but you ain't got to the right distance. You're on the right road, but you ain't got the right avenue. Go.
You can put like a marker line.
Well, if he didn't want to put a marker line, he could. It's very essential, the same thing, without a marker line. He can look at it and tell whether the quarter spot is, right? Does that make sense? Because, see, it's volume, right? And as you take things out, what's going to happen to the stuff? Go down, right? And it should mimic about the same all the way across it. No matter how many times you fill it up, it should drop, right? Things are emptying about the same way. So the look of it should be about the same. He can gauge it, eyeball it, about where on the glass a quarter is, right? So that he can get very, very, very precise without having to put a marker on it. He could, but it's a sphere, right? Or somewhat of a sphere. Kind of whoppy jaw sphere, right?
I have an idea.
What?
Maybe he can have like a coin bank on the inside. Like there's like the coin bank in the inside. So maybe he could have it instead of like just a regular container. It could be like there's like a scale in it, and then
You could weigh it. Yeah, you could weigh it. That's one way. But what would be another way? If he didn't want to look at it, what could be another way that the individual could gauge when he needed to go check it? Go. No. You have to pull the coins, and if you pull the coins, but how do you know when to pull the coins? Go. Hey guys, I fill it up day one. If it takes 4 days, then I'll go, okay, it's 4 days to get to that amount. I'll start looking at how many days it takes to get that much candy. So I can say every third day I might need to do what? Empty it, right? Does that make sense? So you could gauge it by that as well. It is, yes.
I don't think that's a very good way.
Why?
There's different amounts of people every.
I know, but on average, could he do it? I mean, it wouldn't be as precise as looking at it, right? Engage it, because that's kind of like creating a marker. But couldn't he get where he's used to going, hey, every third day I need to do this? Yeah, I mean, think about y'all. Do y'all get set up in routines on stuff? Every so many days you're doing something?
But yeah.
Oh, my bejeebies. Huh? I mean, how many of y'all have animals? Hey, how many of y'all have animals? And you gotta feed and water them, right? So if you got water in a thing, listen. If you got water in a thing, in like a container that flows out based on the drinking, can't you get yourself set up on a schedule of every other day or every so many days you need to fill it up? Yeah, you do that. Yeah, you do. It's that little mental reminder, right? Ting, ding, ding, go look, right? Okay, so here's what I got. I have, I do not know how to count, so please don't remind me of that. I know, I'm sick, so I'm passing this out to get you sick. You know, they say sharing is caring, right? Huh? Okay, ladies and gentlemen, any questions? I'm about to put up the answers to last night's homework so you can check those if you like. Okay. This is homework, right? There you go. Ladies and gentlemen, here you go. Was it 1-3 or 1-2? 1-2? Okay, there you go. Look. Check your homework from last night, ladies and gentlemen. Yes. Y'all need to quit taking extra copies of this. I know I counted out right. Check your homework. We get to the right side. Oh, you got to do that for homework. Well, you need to check your homework from last night. We need to make sure you. What do you get? So what's your question? I can't hear if y'all talk. Function. Yeah. It's function notation. It's Euler. E-U-L-E-R. Back in the 1700s, he came up with shorthand, and that's how you express functions. You can write it in terms of function notation. F of n or f of something isn't a y. See? F of 10 says when 10 is the input, what's the output? This says f of n equals 32. When the output's 32, what is the input? That's what it's saying. So you need to make sure that you're solid on that. Yeah? What do you mean? You don't get it. Hey, y'all see that right over there? I wrote it on the board yesterday. F of n equals 5. If the output is blank at 5, what is the input? Right? I wrote that yesterday, did I not? Why do you think I wrote that yesterday? All this is doing is, what is the value of f of n minus 6? Well, n minus 6, well, that was 8. 8 minus 6 is what? 2. You got to find what n is to answer to b. So f of 2 is negative 3. All you're doing is manipulating it, finding what values go what, right? Yeah. Hey, you got to make sure you jam up jelly tight on this. I'm here to tell you. What? You don't what? Come on. You find the value of the fourth term is 19. How? By adding what? I just showed you. I just told you.
I got 151. What I do wrong? I didn't add it.
Why did we add 7?
Oh.
If the equation goes down, look, dude, look. If that goes to 0 and that goes by 1, this goes by 3, then 0 term is what? 7, dude. 3 times what? 3 times 1 is 3. But I need 10, so what do I got to do to the equation? Add what? 7, right? Yeah? I know it does that. What do you mean you still can't get that? Explicit and recursive is a type of arithmetic sequence representation. It's a type of equation. The explicit will allow you to find any term whatsoever, anytime. The recursive only will allow you to find the next one, given that you have the previous one. That's its only purpose. What's a 0 term? Okay, I'm up here talking, and you're not tracking. If you're not tracking on me, then you're going to be missing the boat. If these are moving by 3, if I back up 3 from 10, I'm at what? Yeah, we've done tables. Come on. Come on, guys. What? All right. Which one? The first part or this part? Up. Go away. Now, where? Like this? This says when the output is 12, what is in? That's how you read that. Because they want to know what in will give you what? 12. So FN, find me 12. Boom, 12's there. So the in that gives me 12 is what? Baby, all these right here. Like this right here says, what's the value of FN minus 5? Well, n is 5. 5 minus 1 is what? 4. So when I go to 4, what's the output? Where? Oh, I ain't on the paper I just gave you. I need you to go home and do that.